Smog is pretty nasty stuff, and I was watching the Olympics and I saw them talking about the smog in Beijing, and I thought, well, it seems like a good opportunity to talk about it here on the Chemist Corner. Now, smog comes from, it's just a mixture of smoke and fog. Okay, that was traditionally what smog was back in like the 1900s and stuff. That's when the term was coined in the late 1800s, and it meant smoke and fog. The smoke from the coal had a lot of sulfur in it, and it reacted with the water vapor and the smog, and basically you were breathing high sulfuric acid. And 4,000 people died in 1953 because of this type of smog. Okay. But the Clean Air Act and things like that, they cleaned up their coal, and they don't, like London doesn't have that problem anymore. But what we have now is what we call photochemical smog, and it's of a different variety, and it actually, instead of having fog, there's no fog involved into it. It's actually in a dry area. What happens with photochemical smog is you have nitrogen oxides are formed in the combustion of your engine, okay, and also some industrial processes. Sure. This nitrogen oxide forms with what they call VOCs, or volatile organic compounds, which, methane is one of them. There's lots of, paint thinner, all sorts of stuff that comes up. And it combines with those and forms peroxides and ozone. Okay, and it's nasty to smell. And here is some nitrogen compounds that, this is copper, and I'm putting some nitric acid. I don't have time to make photochemical smog, so I'm going to make my own little smog here out of this. And this is really nasty to breathe, but this is where this brown color comes from. You can see that. Sure. Okay, and that's the reason why it's got a brown haze to it. It's really nasty, which is why I have it sitting over here. Now, the reason why you have areas like Los Angeles and Beijing that have these problems is because they sit in a bowl, and then you get these temperature inversions that take place, and you get warm air up on top and cold air down on the bottom, and the warm air traps the air in there as long as there's no wind, and so then these pollutants build up and becomes a problem, and you get this brown haze that goes all over. Chicago doesn't have this problem for the most part because the winds just keep blowing it, and it doesn't sit in a bowl. Right. That's right, and so this is photochemical smog. Well, this is the result of photochemical smog. These nitrogen oxides, and it's really, really nasty to breathe, and that's the reason why these guys are wearing the mask. I'm not really sure that the masks really help them out because it's a gas, and it's just going to permeate through. But I suppose it made them feel better.
As you would be aware from the nitrogen cycle, nitrogen requires large amounts of heat to split and bond with oxygen. So we're talking about N2 plus O2 goes to form NO. This happens in the engines of cars during combustion because there's large enough energy in the car to make this occur. Nitric oxide escapes into the atmosphere with some other unburnt hydrocarbons via the exhaust system of the car. So from the exhaust system of the car, we get the nitric oxide plus the unburnt hydrocarbons. The nitric oxide then goes into the atmosphere, and here it bonds with oxygen to form NO2. This secondary pollutant is very reactive in the atmosphere. So the NO2, or nitrogen dioxide, reacts with wavelengths less than 400 nanometers from the sunlight. So the solar radiation coming in, the NO2 absorbs it, and it undergoes photochemical dissociation. So we end up with these two things from breaking it. So from here we've got an NO going to here, plus an oxygen here. This oxygen can form another secondary pollutant, ozone. So we get O2, add O, going to form ozone. Intense sunlight, or the HV, is crucial in this process, and the molecules need to be almost stationary for this to occur. So windy days moving the smog around is not ideal for these conditions, but really still hot days will make these reactions occur. So let's recap. Primary pollutants are those that come out of the exhaust of the car. So we have carbon monoxide, carbon dioxide, sulfur dioxide, unburnt hydrocarbons, and nitrogen oxide. These primary pollutants in the atmosphere with light of less than 400 nanometers form the secondary pollutants. So examples of our secondary pollutants are ozone, nitrogen dioxide, nitric acid, and sulfuric acid. Photochemical smog has some harmful effects, particularly when we're talking about oxides of nitrogen and ozone itself in the troposphere. Ozone itself attacks double bonds, particularly in long-chain molecules like rubber. This breaking of the long-form chains makes cross-linking between the chains, and it causes cracking in rubber, which makes it perish quicker. At concentrations of greater than 0.15 ppm, ozone causes severe health problems such as coughing, wheezing, and irritation of the bronchial tract. So this is more generally known as respiratory system issues. Plants also suffer when there's excess ozone in the atmosphere. Their leaves become yellow, and the rate of photosynthesis is reduced. Catalytic converters are a really important part of minimising our primary pollutants in the atmosphere. In internal combustion, it only takes a few milliseconds. This results in both complete and incomplete combustion. It's the incomplete combustion that gives our primary pollutants. The role of the catalytic converter is to remove the primary pollutant of CO, HCs, the hydrocarbons, and NO, and it does this by converting them into carbon dioxide, H2O, and pure nitrogen. Catalytic converters are made of expensive metals such as platinum, palladium, rubidium, and they're coated on the surface of a ceramic honeycomb structure like shown in the picture. They can be used at really high temperatures, up to 1300 degrees Celsius, and the structure of it allows for the flow of exhaust gases through it and provides a large surface as a metal catalyst to remove the primary pollutants. This diagram shows an example of that process happening. So you can see here we've got the honeycomb structure, primary pollutant gases are moving in, they're being removed here, and our more desirable gases are moving out. Let's have a look at some of the equations that make this happen. If we take the removal of carbon monoxide, so we have carbon monoxide, some oxygen, and we get carbon dioxide. This is our more desirable product, and CO would have been our primary pollutant. Carbon monoxide can also bond with water to give carbon dioxide and hydrogen gas. The removal of hydrocarbons can also happen with oxygen. So we have our primary pollutant being converted into our more desirable carbon dioxide and water. Similarly, we can have our hydrocarbons with water and we get carbon monoxide and hydrogen. If you have a look at this equation, we can see our primary pollutant has actually produced another primary pollutant on the way out. So this is not an ideal situation. If we have a look at the removal of NO, we can see that we have two primary pollutants combining and we get two more desirable products, one in nitrogen and the other in carbon dioxide. We can also have the NO combining with hydrogen and we get water and nitrogen. So again, our primary pollutant is converted into more desirable products. Check out the video of what goes on in a catalytic converter at an atomic level. There are three main factors that affect the efficiency of a catalytic converter in reducing carbon monoxide, nitric oxide and hydrocarbons. The first of these is temperature. There needs to be an effective temperature for this reaction to occur, or the efficiency of the catalytic converter to take effect. So at low temperatures, the catalytic converter is extremely inefficient. So that occurs such as times when you're starting up your car. As the catalytic converter heats up through to the running of the engine, the percentage of conversion gets greater and greater and increases to greater than 95% when the car reaches temperatures above 400 degrees Celsius. The percentage conversion of pollutants is shown in this diagram. So we can see that at low temperatures, the percentage conversion is also low. The optimum temperature for conversion starts at around 320-330 degrees, and at 350 starts to plateau. So for higher temperatures, we're getting a much higher conversion. You can see also that for hydrocarbons, we don't get a full conversion. It plateaus out in the 80s, but that's much better for carbon monoxide and nitric oxide. The oxygen concentration in the exhaust gas mixture is also significant in making sure the catalytic converter is working correctly or efficiently. So as you would remember, that removing these pollutants often required oxygen. So that comes from this gas mixture, and it's measured by an oxygen sensor. If necessary, the oxygen sensor adds in more oxygen from the air to ensure that the catalytic converter is continuing to work effectively. Just like in the previous example, we needed to make sure that the oxygen concentration was high enough. We also don't want the air concentration to be too high, because there's an optimum ratio of 14:6:1 to ensure that we have the right ratio of our pollutants to our air, because we need to make sure that we have the right ratio of pollutants and air. At higher ratios, the percentage of nitrogen oxide converted decreases really sharply. At lower ratios, the percentage of conversion of the carbon monoxide and hydrocarbons decrease. So it's a bit of a juggling act. That's shown a bit more clearly in this graph. So you can see that as we increase the pollutants to our desired point, the carbon monoxide conversion rate increases gradually and then plateaus. So our optimum part for our carbon monoxide is there. Similarly, our nitric oxide has a fairly high conversion rate until this point here where it decreases significantly. And our hydrocarbons have an optimum rate here, but that starts to affect the other two. So we bring it back to the middle where all of the others meet, and that's our optimum ratio. Let's have a look at how this looks with the catalytic converter. So we have our input. We have air, which is made up of nitrogen and oxygen, and we have the fuel with the hydrocarbons. This then goes into the engine at high temperature. We then get our two combinations. We then get our complete and incomplete combustion. Then goes into our catalytic converter, and from there we get N2, CO2 and H2O. Let's recap and connect all of these ideas to where they fit in the intended student learning outcomes from your subject outline. The first of these outcomes is to write equations for the formation of nitrogen oxides, particularly NO and NO2. And particular note that nitrogen oxides are formed in high temperature engines and furnaces. The second is to describe and write equations showing the role of nitrogen oxides in the formation of ozone in the troposphere. So here, you need to be able to use the equations, but you also need to be able to describe the process. The next outcome is to explain the terms primary pollutants and secondary pollutants, particularly with reference to the harmful effects of nitrogen oxides and ozone in the troposphere. It's important to note here that ozone is critical in the higher levels of the atmosphere, or the stratosphere, but it is detrimental in the troposphere. And the final outcome for 1.5 on photochemical smog is to describe how catalytic converters reduce the quantities of nitrogen oxides generated by cars. The high temperature, the platinum catalyst, and the large surface area made by the honeycomb structure are important in this as well.